Imagine a silent visitor, the size of a Manhattan skyline, slipping through the darkness between the planets, cold, inscrutable, and carrying with it the chemical memory of another star. For a long time, such wanderers were the stuff of thought experiments and a handful of odd detections, Oumuamua and Borisov, fleeting traces that teased astronomers and then vanished. Now imagine that what we thought was a rare whisper has become a conversation, 5 whispers, all speaking from roughly the same part of the sky. This is the story of 3I Atlas and its newly discovered companions, a discovery that forces us to rethink how planets, organic matter, and even the potential seeds of life move through the galaxy. From the moment researchers flagged 3I Atlas, instruments and imaginations were captured. At first glance it could have been another odd comet or a rogue chunk of rock. But the James Webb Space Telescope, our quiet sentinel parked at the Sun, Earth L2 point, peered at it in wavelengths old telescopes could never properly see. Webb's infrared sensitivity did more than reveal one strange object. It revealed a family likeness, faint thermal glows where comets typically show only reflected sunlight, spectral fingerprints laden with unexpected organics and silicates, and motion that didn't always obey gravity's textbook rules. Then Webb found 4 more objects with the same peculiar signatures. The discovery shifted the frame from anomaly to pattern, and patterns in astronomy almost always mean story. What does that pattern tell us? First, the objects share a set of common traits. They emit thermal radiation inconsistent with a simple icy comet warmed by the sun. Their spectra, those tiny bands of light that betray chemical identity, show signals of carbon-rich compounds and crystalline silicates. In ordinary interstellar dust or in the Kuiper belt objects of our own system, we see a certain palette of materials. These visitors carry a different palette, textures and molecular notes that suggest processes of heating, irradiation, and reprocessing over cosmic time. Instruments aboard Webb, near-infrared and mid-infrared spectrographs, mapped minute emission lines, revealing a repeating chemical motif across all 5 bodies. When separate observatories on the ground checked the signals, they found the same story, though none could match Webb's depth. Together, those datasets turned possibility into probability. These were not random wanderers but fragments with a shared past. The trajectories deepen the mystery. Each object follows a hyperbolic path, a one-time visit through our solar system, not a bound orbit. Trace those paths backward in time, and they converge toward a general quadrant near the constellation Lyra, close to the line of sight toward the star Vega. The odds that 5 such objects would independently enter our system from the same direction are vanishingly small. Instead, the coherence of their incoming vectors argues for a common origin, a violent event or a structured debris stream somewhere in that region of the Milky Way. Vega's neighborhood, or at least the Lyra corridor, is known to host dense fields of stellar debris and protoplanetary disks. It's a place where, over millions of years, gravity and explosions can rearrange planetary systems and fling fragments outward. The implication is profound. Our solar system may be passing through a ribbon of debris, a galactic current of material carrying the bones and ashes of other worlds. That ribbon analogy matters because it changes how we picture interstellar space. For decades we imagined the vast emptiness between stars as a thin soup, dust, gas, and radiation sparsely distributed. Webb's findings suggest the soup is laced with currents, solid, kilometer-scale remnants of planets and moons that once orbited other suns. If fragments of planetary systems traverse the galaxy regularly, they become a mechanism of material exchange on an enormous scale. Rocks, minerals, and organic molecules could cross star systems, carrying chemical stories from one birthplace to another. For astrobiologists, this is electrifying. Spectra from 3I Atlas and its companions show carbon-based compounds and complex organics, ingredients, not evidence, of life. But ingredients are everything in chemistry. If icy fragments carry complex organics from one system to another, panspermia moves from idle speculation to plausible mechanism. Peering at composition is like reading a foreign language's handwriting. Isotopic ratios, crystalline structures, abundances of oxygen and metals, these data encode the environmental history of a fragment's origin. Webb spectra hinted at unusual isotopic values and silicate crystal morphologies not seen in our solar system's catalog. One object's mid-infrared glow suggested internal heating greater than expected for a small body drifting alone through interstellar space. Radiogenic decay, tiny amounts of heat released by long-lived isotopes such as potassium-40 or formerly abundant aluminum-26, could explain a faint internal warmth. That would mean the fragment was born in the early, most volatile centuries of its parent system, a time when planetary embryos still carried significant radiogenic heat. In other words, some of these fragments might be genuine time capsules, frozen records of the physical and chemical conditions of worlds that formed around other stars billions of years ago. Other details deepen the portrait. Webb's long-term tracking showed changes in brightness and thermal output as these travelers approached the Sun. Some display faint, comet-like tails, motorless ribbons of sublimating ice, while others remain dark, inert, and rock-like. One body's surface looks coated in tholin-like materials, organic residues formed by cosmic rays and ultraviolet radiation that impart red hues and sticky chemistry. Another shows faint cyanide absorption bands, another hints at methane ice mixed with silicate dust. Yet despite these differences, a core molecular fingerprint repeats across the group. That commonality suggests either a common birthplace or a similar formation process operating under common conditions. Either way, the spectrum pushes us to treat these objects as data-rich specimens rather than inexplicable oddities. The shapes and spins tell a story too. Light curves, tiny fluctuations in reflected or emitted light as a body rotates, reveal elongated, irregular silhouettes tumbling through space. Periods range from a few hours to days, and their rhythmic flickers imply non-spherical, fractured shapes. These aren't fluffy piles of ice and dust, several show spin stability inconsistent with loose aggregates, indicating internal cohesion. Survivors of violent ejection events, they appear to be fractured fragments of larger, differentiated bodies, pieces of moons, dwarf planets, or even shattered exoplanets whose interiors once separated into metal cores and silicate mantles. The colors and contrasts across their surfaces, bright patches of reflective ice beside dark, carbon-rich crusts, suggest layered histories of impact, thermal processing, and long exposure to cosmic rays. Imagine a world torn apart, its fragments scatter across the galaxy for eons, and those fragments eventually brush past another star, telling the tale of where they came from through their spectral accents. But how are such fragments launched into interstellar space? Several mechanisms stand out. Young star systems often form in clusters, crowded neighborhoods where close encounters between stars are common. A passing star, a giant planet's gravitational shunt, or the chaotic dynamics of a congested protoplanetary disk can slingshot bodies to velocities that allow them to escape their birth star's gravity well. Cataclysmic events, a supernova shock wave, a stellar merger, a destabilized planetary system, can also hurl debris outward with violent efficiency. The energy required to accelerate multiple large fragments to interstellar velocities is enormous, so the presence of 5 coherent fragments implies a major event, a regional catastrophe or a dynamic highway carved by gravitational forces. That highway could be a galactic tidal stream, a corridor shaped by the Milky Way's gravitation and the motion of spiral arms, concentrating debris along certain trajectories. If interstellar debris streams are common, the consequences ripple through astrophysics and cosmology. The population of such objects might be large enough to matter in the galaxy's mass budget, altering how we account for the distribution of solid matter. Their chemistry provides direct samples of exoplanetary material in ways no telescope can fully substitute. By analyzing these fragments, astronomers can indirectly sample the chemistry, thermal history, and evolutionary pathways of distant planetary systems. It's like finding a shard of pottery on a beach and reconstructing the civilization that made it. The isotopic signatures could tell us about nucleosynthetic environments. Was the fragment formed near massive stars that enriched the region with heavy elements? Or did it arise in a younger, metal-poor neighborhood at the galactic outskirts? Each answer expands our map of how the Milky Way assembled its diverse family of stars and planets. There is also a tactile, almost human side to this discovery. For millennia, humanity looked up and saw only light. Now we intercept physical emissaries bearing tangible matter from other stars. The emotional collision is unavoidable. These objects are cosmic mail. They carry amino acid precursors, phosphorus traces, organics, and elemental patterns that might help seed the chemistry of life elsewhere. One Webb observation hinted at trace amounts of phosphorus, a notoriously hard element to detect at interstellar distances, yet crucial for biological molecules on Earth. This doesn't mean biology lurks aboard these fragments, but it does mean that the elements necessary for complex chemistry appear to be common across the galaxy. The raw materials of life, scattered like cosmic pollen, could arrive at many different worlds across geological time. As the Webb team refined their observations, timing sequences, thermal maps, rotational light curves, subtlest anomalies emerged. Some objects showed a faint mid-infrared excess inconsistent with mere reflection, others exhibited crystalline silicate bands that suggest heating and cooling cycles absent in most interstellar dust. These clues point toward environments with alternating thermal histories, perhaps bodies that orbited in systems with eccentric giants, or fragments periodically blasted by stellar flares and then plunged into frigid darkness. The diversity among the 5 objects suggests that whatever event created them was complex, a single planet shattering, a chain reaction of collisions, or a more diffuse process like the slow erosion of a disrupted protoplanetary disk. The implications reach beyond chemistry. If fragments travel between systems on a galactic scale, then planetary systems are not sealed ecosystems but participants in an exchange network. Over billions of years, matter can migrate from star to star, carrying the chemical signatures, and possibly the prebiotic complexity, of one system into another. In terms of cosmic evolution, this exchange reshapes how we think about habitability. Earth is not an isolated cradle, it is one node in a network where ingredients of life are redistributed across the Milky Way. That network may not guarantee life will bloom wherever these fragments land, but it increases the chances that the raw ingredients arrive in many locales. Scientists react to such discoveries in 2 ways, with disciplined skepticism and with childlike wonder. The skepticism is methodological, every spectral line must be scrutinized, each orbital simulation refined, and alternative explanations tested. Webb's positioning at L2 allows precise, repeated monitoring without atmospheric noise, an observational advantage that ground arrays cannot match. Astronomers are building spectroscopic inversion models to decode the precise chemical abundances and to simulate the thermal and mechanical histories of each fragment. Each refinement is a step from mystery toward mechanism. And yet even as the data tighten, the human heart responds to the poetry of it all. The garden variety of our imagination, stories of alien artifacts, of cosmic messages, meets hard data in a way it rarely does. Professor Lowe's early musings that 3I Atlas might be scoping us out were speculative, and the evidence does not demand biological or technological explanations. But the discovery of a cluster of interstellar objects, all sharing a chemical likeness and a common incoming direction, does suggest that the galaxy has structure, circulation, and perhaps an archival memory written into the trajectories of rocks and ice. Where does this leave us? For now, it leaves us with questions that will drive years of observation. What precisely formed these fragments? How frequently does interstellar material stream through our system? How common are the complex organics Webb has detected? Are there other corridors of debris elsewhere in the Milky Way? Will we someday be able to rendezvous with one of these fragments, send a probe to sample a piece of another system firsthand? Each of those questions is both technological and philosophical. They demand improved telescopes, better orbital models, and patient curiosity. They also invite us to consider our place in a galaxy that is more interconnected than our old mental maps allowed. The discovery of 3I Atlas and its companions marks a new chapter in cosmic research, from seeing distant light to catching distant matter. Webb's instruments transform the invisible into the tangible, exposing a dynamic interplay of formation, destruction, and migration that stitches stars together. As more data arrive and models sharpen, we will refine the portrait of these visitors and perhaps uncover the story of the system that birthed them. For now, these objects are part puzzle, part poetry, shards from elsewhere that remind us the galaxy is not a quiet museum but a restless, migrating archive of material, of chemistry, of history, and of possibility. So look up tonight not only at the stars but at the idea that between them there is motion, objects on long voyages, carrying within them the memory of other suns. Each passing fragment is a messenger, and with every messenger Webb catches, humanity gains a new line in the cosmic story.